It's now time to look at solving equations that involve trig functions. When you're using trig algebraically in other disciplines, you're always having to deal with situations, word problems, whatever. There's a equation that needs to be solved. So notice the difference, though. First of all, in the following two equations. We've talked about this before when I introduced identities, but I want to point it out now that this equation right here is an identity. This is true for every single value of x. I don't care what x is, you plug it in, you add 3 to it, you multiply by 2. You're going to get the same result as taking the same value of x, multiplying it by 2, and then adding 6. That's an identity. As opposed to an equation like this, which is not an identity. Some values of x make that true, other values of x make it false. And on something like this, this is when we say solve the equation. You want to find the x's that make it work. Which x's make this true? Well, I mean, you've been doing linear equations for a long time now, right? You add the 2 over, you get 3x equals 5, you subtract the 2, that is, and then divide 5 minus 2, and then you divide by 3, so x is 3 divided by 3, which is 1, right? There's only one value of x, and it happens to be x equals 1, that makes that equation true. Right. So we're going to be doing similar things now with equations with trig functions involved. If I said 2 times the sine of x plus 1 is equal to 0, could we solve for x? Well, on something like this, what I do first of all, there's one trig function involved, is I solve for the trig function first. So move the 1 over, divide by 2. So I have the sine of x equals minus a half, and then I've got to figure out what x is. There's a similar problem over here that if I said 2x squared, well, I'm going to do it with a minus 1 equals 0. How would you solve for x? Well, you move the 1 over, divide by 2, and now you've got that x underneath or inside of a squaring function. What you got to do is get it out. So how do you get rid of a square? Well, you do the inverse thing. You do the inverse. You take the square root. Right, so this would be square root of 1 over the square root of 2 would be x. Actually, plus or minus, come to think of it. There's two things when you do that. Likewise, you know, how do you get this x out of the sine? Well, you have to do the inverse of sine. So x is sine inverse of minus a half. Now, like this one, where the cosine, where x squared isn't really invertible, but we do the square root, we have to realize that, oh, there's two possible answers. Well, with the inverse sine, I mean, sine's not really invertible. There's lots of possible answers. Inverse sine only gives us one of them. Now, there are times when the number in here is not particularly nice, and you're just going to type it into your calculator, sine inverse of whatever that is, it's going to give you an answer. There's other times when you might recognize that, oh, I happen to know that I've got a sine equal to negative 1 over 2, and so x is equal to, I recognize this is the 1, 2 square root of 3 triangle. That's a pi over 6 angle, but it's negative, so minus pi over 6 would be my answer here, one of my answers. If you ask your calculator what's the sine inverse of minus a half, it's going to give you this answer. It's going to say minus pi over 6. It may give you it as a decimal form of that, but still, that's what it's going to give you. There's other angles, though. In fact, any angle coterminal with that would also be a solution. So if I went around this way, that would be 11 pi over 6. Or if I went around again, that would be 23 pi over 6, and so on, right? Actually, I think I can describe all of those as saying minus pi over 6 plus 2 pi n, where n is an integer. And notice by integer I mean both the positives and negatives, so n might be 0 or 1 or -1 or 2 or -2. So I can either be adding 2 pi on, go around again, or I might be subtracting 2 pi or multiples of 2 pi if n is negative. There are, however, more answers to this than just those, because that's not the only place where the sign is equal to -1/2. There's also the situation where you might be over here in the third quadrant, -1/2. Right? And so now I'm looking at that angle. Well, that angle is a pi/6 more than pi, so this must be 7 pi/6, or anything coterminal with that. So to get all the rest of those, we do this. Now, I should point out that in the trig book that we've been using, this is section T 6.1. Okay. In the pre-calc book, which we haven't really used much at all yet, but we're going to start using, this is section PC, so pre-calculus book, section 9.5. We'll be doing 9.5 and 9.6 for graphing equations, not graphing equations, solving equations. So the answers here are a bunch. There are all of those that are coterminal with -pi/6, and there's all those that are coterminal with 7 pi/6. Now, graphically, let me look at this problem again here. At this stage right here, I have sine of x equals -1/2. I know what the sine curve looks like. The graph of y equals sine x looks something like, something like this. And to say -1/2, down here, here's the line y equals -1/2. The solution of pi/6, sorry, -pi/6 is right here. Where this crosses right there, that x value is -pi/6. Now, if I had just said pi/6, sorry, -pi/6 plus 2 pi, I'd be talking about this one and then that one. And minus pi would have been this one back here. What I see is that as I add on 2 pi, as I add on the period of the sine curve, I'm getting just the answers that are on the uphill part. But there's these other ones that are on the downhill part. So even if I hadn't thought of this initially, I quite often will look at a graph and say, am I seeing the whole picture, right? I know what the graph of sine x, sorry, y equals sine x look like. I know what the graph of y equals -1/2 looks like. And I can see that there's more intersection points than just these. So then I go back and say, well, how do I find those? Where's that other thing? It's like, well, looking over here, here's from 0 to pi/2, that's all first quadrant stuff. From pi/2 up to pi, that's second quadrant stuff. So it seems like there's something happening here in the third quadrant that I might have overlooked. And there I can see it. Okay. So there's my first example. I'm going to do a bunch of videos, I guess, with a bunch of different examples, but I want to keep them reasonably short. So example number 1.